What? Okay.
Whatever you say.
So, one of the things one of the types of problems we've already done is like the weight percent problem, like weight percent sucrose in a sugar solution. Well, this is sort of like that. It's a weight percent analysis of a compound. So it's called percent elemental composition. Elemental meaning the elements, and you're dealing with a compound. So bottom line, it breaks down, for instance, water, we would come up with a weight percent that the hydrogen bring and a weight percent that the oxygen bring. That's it. Okay. Percent elemental composition deals with, kind of takes a compound and says it's like a mixture. So that's how much weight is brought by each element. So if you're given the formula of the compound, you can definitely knock that out. No wonder this isn't working. Not plugged in. Students usually do pretty good with this. So we could knock out the weight percent of acetone. We need to see how much weight is brought by carbon, how much weight is brought by hydrogen, how much weight is brought by oxygen. There's different ways to skin this cat, but I kind of like this way, where you guys just recently calculated molar masses. So let's knock out the molar mass for acetone. The molar mass for acetone. So the formula is C3H6O. So we have 3 times 12.01 for carbon, plus 6 times 1.008 for hydrogen, plus 1 times 16.00 for oxygen. So 1 mole of acetone will weigh 58.08 grams. Cut this out. All right. So we kind of took it as a 1 mole basis then. In 1 mole, that's the mass of acetone you'll have. Well, the amount brought by each element is this, where simply the carbon is 3 times 12.01. The hydrogen is 6 times 1.08. The oxygen is 1 times 16.00. Okay? So if we want a weight percent of each of those, what you're going to see on the next slide is simply to take these individual masses and divide by this mass. So it looks like this. For carbon, the weight percent carbon would be that 3 times 12.01 divided by 58.08. I guess I should say 3 times 12.01 grams carbon divided by 58.08 grams of carbon. To get it, that if we just did that, that would give us what, a kind of a mass fraction. So to give it parts per 100, we multiply by 100%. We round to 4 significant figures. It's not random, it's 4 there. So what I got was 62.04% carbon. We do a similar thing for hydrogen. In the numerator for the mass percent of hydrogen, we're going to take 6 because that was the formula, times 1.008 grams of hydrogen. We're going to divide it by the mass of 1 mole of the compound, 58.08 grams of C6H6O. Again, times 100 to get it to parts per 100. Round to 4 sig figs, it's got 10.41%. Now here's where sometimes students say, well, can't I just take 100 minus the sum of these two to get to my weight percent oxygen? And you could. But why, if you're on a roll? So we can do the same thing with the oxygen in the numerator. We'll put the mass brought by the oxygen, which is 1 times 16.00 grams of oxygen, divided by the total mass of 1 mole of compound, 58.08 grams of C3H6O. Get it parts per 100 times 100, or 100%. Give us 4 sig figs, and you get 27.55%. So if you're given the formula for any compound, you can come up with the weight percent of each element this way. Not too bad. It's kind of a straightforward sort of problem. Now, if you add those up, they should be equal to 100, right? If you do a problem like this, it's a good check. Doesn't mean you necessarily got the right answer, but it kind of gives you confidence in your answer. The other thing, though, is if you're off by, you know, 0.05%, you know, if it's 100.05 or 99.95, it's probably okay. It's just in rounding, so that's okay. Well, we can do another problem kind of related to weight percent. It's coming up in a minute. Before I talk about that, I need to talk about these two different types of chemical formulas. You're probably used to kind of you're probably used to the molecular formula where it gives you the real number of atoms of each type of element in that repeating unit of a molecular compound. There is this other thing that comes in handy for compounds called its empirical formula. Empirical formulas sometimes, how do I say this? Molecular formulas, I put it that way. Sometimes molecular formulas can be reduced to give you a different formula we call an empirical formula. So there's a reduction that happens. The difference between the two is that you will find that the empirical formulas, you can't divide the set of subscripts by a whole number and get another set of whole numbers. So it's easier to show you. Here's an example. We have butane. The real deal for a butane molecule, it will have 4 carbons and 10 hydrogens. That's the real deal for a butane molecule. So we can take 4 and 10 divided by 2 and get 2 and 5. So the reduced formula, the empirical formula, is C2H5. Water, the molecular formula is H2O. Its empirical formula is H2O also. Hydrogen peroxide, it's the Santa Claus empirical formula. So hydrogen peroxide, H2O2, of course we can divide each of these by 2 and it reduces to empirical formula of HO. Hydrazine, N2H4, reduces to empirical formula of NH2. We can divide these subscripts, both these subscripts by 2 to get 1 and 2. My favorite are coming up. These two are my favorite. So acetylene is got carbon, triple bond carbon, and hydrogen scooting out like that, C2H2. And it's can be reduced to an empirical formula of CH. Benzene, and I don't know if we've talked about benzene in here, it's that ring compound. It's got 6 carbons in a ring and it alternates single, double, single, double, single. So it's got 6 carbons and 6 hydrogens. So it actually also reduces to the same empirical formula as acetylene. I think that's.
So how do you differentiate between the two if you're doing the problem?
Well, it's cool because you'd have to be given enough information in the problem to differentiate. I will tell you that if you do, it's called and we'll talk more about this, like a combustion analysis where you take acetylene and in a separate combustion analysis you take a benzene, and you're going to come up with the same relative numbers of carbon to hydrogen, just 1 to 1. So just from that combustion analysis, you can't tell which is which. So that answers your question. The other piece of information we'll talk about in a minute is if you have the molecular weight, like the weight of the entire molecule, whether it's acetylene or benzene, you'd be able to tell that right in a snap. So you need to have more information. For ionic compounds, we said that they don't exist as molecules, they exist as formula units, FUs. And the formula units are generally already kind of in their lowest form. So the ionic compounds are usually already listed as an empirical formula. So we've talked about 2 things already in our short 5 minutes here this afternoon. Okay, we talked about weight percent, and that's the relative amount of each element in terms of mass. And then we talked about empirical formulas, which is the relative number of each type of element in terms of relative number of atoms. Okay, it's like a reduced formula, oftentimes reduced from molecular formula. So I'm going to show you how actually you can go back and forth between these two. Going from like a CH, you guys could go to the weight percent carbon and weight percent hydrogen from that, couldn't you? And again, I'm telling you, it's not stretched, that if you do acetylene, if you do benzene, there's going to have the same mass percent. So you can calculate the percent elemental composition from the empirical formula or the molecular formula. But what I want to show you is that if you were given weight percents, relative masses of each element, or do this sort of problem where you go from weight percents to the empirical formula. That's the next type of problem I'm going to show you. So let's take an example. Let's say somebody did the analysis. We have a compound that contains carbon, hydrogen, and oxygen. There's a lot of compounds out there like that. And here by weight is how much carbon there is, how much hydrogen there is, how much oxygen is. It's by weight though. It's not, you can't take that directly and turn them into subscripts, relative number of atoms of each type of element. But we're going to get there. In chemistry, in a lot of types of chemistry problems, it's helpful to go ahead and have a starting point. It's called a basis. And you get to pick your basis. It's not a B-A-S-E-S, it's a B-A-S-I-S, not baseball. Okay, you get to pick what you want your starting point to be. So in this case, if we assume 100 grams, 100.0 grams, so 4 sig figs of the compound, it's a beautiful thing because then we can take those weight percents and turn them into grams. That's our starting point. Sometimes people say, well, Mrs. Snipes, how can you start that as a basis? Because I know working this sort of problem, it works well. The next step then in working this problem is to take those grams and to get into relative numbers of moles. We know that we can take those grams and convert them to moles using the periodic table and the molar mass for carbon, hydrogen, and oxygen. So for carbon, it looks like this. We take that mass, 53.3 grams of carbon. We use the molar mass of carbon, 12.01 grams of carbon per 1 mole of carbon. Grams cancel, we have moles of carbon. How many sig figs?
3.
Yep, 3 sig figs. So 4.44 moles of carbon. Hydrogen, we're going to take that 11.2 grams of hydrogen, which is what we have, and taking 100.0 grams of the compound. And then we're going to use the molar mass of hydrogen from the periodic table, 1.008 grams per 1 mole. So grams will cancel because I have 1 mole. All right, we'll be left with moles of hydrogen. Again, 3 sig figs. So, relatively speaking, in this 100-gram sample of our compound, we have 11.1 moles of hydrogen. Oxygen, we take the 35.5 grams of oxygen, it's our first term. Use the molar mass of oxygen, which is 16.00 grams per mole. We use the flipped version of molar masses. Grams cancel, we're left with moles of oxygen, round to 3 sig figs. I got 2.22 moles. So the way I think of it is carbon, hydrogen, oxygen. We could take these and make them as subscripts. So we have 4.44 moles, carbon atoms, and we have 11.1, relatively speaking, hydrogen atoms, and we have 2.22, relatively speaking, oxygen atoms. Now, of course, those subscripts are not going to work. So now we basically have to scale those to get whole numbers. I'm going to show you on the board, or I'm going to show you in my notes or slides how I do it, and then I'm going to show you on a board how I do it in a table form. So if we key in on the one that is the least moles, 2.22 moles of oxygen. Oxygen's the least. We're actually going to see what the relative amount of carbon and hydrogen is to oxygen. Oh, before I do that, this kind of says that those subscripts are only relative to our basis, which is 100.0 grams of compound. So again, I'm picking on relative amount to oxygen because oxygen is the least amount. So to get the ratio of carbon per oxygen, I take the 4.44 moles of carbon and I divide it by 2.22 moles of oxygen. And right there, you're probably saying, well, that's a nice, sweet number, and it is. So relatively speaking, if I go with a subscript, hydrogen, oxygen, if I go with a subscript of 1 mole of oxygen, I can already kind of say, well, that must be 2 moles of carbon. Let's do the similar thing with hydrogen. So for hydrogen, we got that whopping 11.1 moles of hydrogen a minute ago. So if I take 11.1 moles of hydrogen, I divide that by 2.22, it might not be as obvious.
5.
Yep, it's 5. So now, based upon 1 mole of oxygen, I have 5 moles of hydrogen. Now that's looking more like an empirical formula. And that's it. That's the empirical formula of this compound based upon that weight percent. Now I like that and all that, but usually when I work a problem, like in my answer keys, it's going to look something like this. It's just a way to organize this sort of problem. And I'll kind of try to show you the benefits of it later. But I make columns, and my first column are the elements. Now you're gonna, when I write on the board, you're gonna see, oh my gosh, I'm glad she uses PowerPoint, because, okay, so I'm gonna put, we have carbon, hydrogen, and oxygen. And my basis is already 100.0 grams of sample. I'll put CPD for compound, 100.0 grams of compound. So based upon that, then I can go ahead and take those weight percents, and that will be the grams of compound. So what we had, 53.5 grams of carbon, 11.2 grams of hydrogen, 35.5 grams of oxygen. Then this is what I tell you not to do, but this is how I usually do it. Right next to my mass column, I go ahead and put a moles column. Okay, and I'm going to take these masses, I'm going to put them over 1, and I'm going to use the periodic table and use the molar mass of these elements, the mole mass of these elements, and I'm going to convert from mass to moles. So like we said a little bit ago, the decimal number of the molar mass of carbon is 12.01 grams per 1 mole. Now I'm a stickler for labeling things, but the other reason I like this is if I label my row, then I don't have to go ahead and put carbon. I'm just like, well, I know that's my carbon row. So down here, we're going to go ahead and do it for hydrogen. So the decimal number for hydrogen is 1.008 grams per 1 mole. And then for oxygen, it's 16.00 grams per 1 mole. I mean, and this is actually what we did a little bit ago. So round it to 3 sig figs, everybody. Of course, I'm going to get those same numbers, 4.44 moles of carbon, 11.1 moles of hydrogen, and 2.22 moles of oxygen. So that's kind of what I do. Then what I do, once I have the moles that are in 100 grams of the sample, I make another column. And at the top of this column, I always say divide by, and I just divide by the smallest. So in this case, I'm going to divide everything by 2.22. That's a column. So of course, 4.44 divided by 2.22 is 2.00. 11.1 divided by 2.22 is that 5. And 2.2 divided by 2.22 divided by 2.22, of course, is 1. And then I have these just ready to go ahead and be my subscripts. So carbon is 2, hydrogen is 5, and oxygen is 1. So that's just kind of how I work the problem. It's the same, there's nothing different. But as you would imagine, the theme in this class is to show your work or explain your work, how you do things. So you're going to want to do that. Cool. Yep, so the empirical formula of this compound, given those weight percents, is C2H510. C2H50. Darn it, you know what I mean. C2H50. Oh gosh. 01. Final answer. All right. So here's the little caution though. Once you kind of do this exercise and you get your numbers over here, be careful as far as trying to round them up or down. Look for what I call the twos, the twos, the threes, and the fours, factors of twos and threes and fours. If something ends in 0.5, it's a factor of 2. I'll kind of show you how that works. You can multiply through by a factor of 2 and get it up. If something ends in something that looks like a threesies, like thirdsies, so that would be 0.3 or 0.67, okay, you're going to multiply by 3 to kind of make that work. 0.25, 0.75, you're going to multiply through by 4. So here are some examples. Let's say that you went ahead and you got a relative number of 1.5 to 1. My suggestion would be to multiply both the top and the bottom by 2. If you take 1.5 times 2, you get 3. If you take 1 times 2, you get 2. Okay? I said look out for the thirdsies. Here's my thirdsies. So if we take 3 times 1.3 and 3 times 1, 3 times 1.3 is 4. 3 times 1, of course, is 3. This would be the foursies, or the quartersies. Take 4 times both of those quantities, and you get 5/4. Okay, and we're kind of back to the thirdsies again. If we take 3 times both of these quantities, we get 8/3. So be careful. In other words, put another way, don't take this guy and round it down to 1. Don't take this guy and round it up to 3. Okay, and don't take this guy and round it down to 1. You can do that, but it's probably something else hiding in your data that you're not, no. I got an example coming up here in a minute, what that would look like. So let's do another compound, and this compound's a little simpler. We only have carbon and hydrogen. And again, I'm going to show you kind of over here how I would do it. We're going to go ahead and take 100.0 grams as our basis. And then that means that our weight percents are really grams. So we're going to take those grams and come and figure out moles. So we can figure out the moles of carbon by taking the mass of carbon, 82.7 times 1 mole of carbon per 12.01 grams, and get 6.89 moles of carbon. We can do a similar thing for hydrogen. So I'll let you write that down. I'm going to make my little chart over here. My chart over here is even, I'll show you why this is nice, I think. Element, mass, moles, only carbon, hydrogen. We had 100.0 gram of compound is our basis. Don't forget to say what your basis is. 82.7 grams of carbon, molar mass of carbon, 1 mole, 12.01 grams. That leaves us with 6.89 moles of carbon. From the weight percent of hydrogen, in this case, we have 17.3 grams of hydrogen. Molar mass of hydrogen is 1.008 grams per mole, 3 sig figs. That gives us 17.2 moles. So like I did before, I'm going to make a column here, and we're going to divide by the smallest. What's the smallest this time?
6.89.
It is 6.89.
Comes up like 2.5 something, or 2.49 or something.
Yep, So this, so in my little world here, of course, 6.89 divided by 6.89 is the 1. 17.2 divided by 6.89, that's my 2.5. Now this was where I said don't round that up. Okay. No. So this is where, to clean this up, we're going to introduce one more column, and we're going to say times 2. And we're going to apply it to each of these relative moles. So of course that leaves that as 2, and then what does this become? 2.5 times 2.
2.5 times 2 equals 5.
Yeah. And these numbers then are ready to go ahead. These are the numbers that are your subscripts. So it's C2H5. On my slides, it looks like this. Like I said, if I were from, there are definitely some problems in chemistry dealing with compounds that it's just kind of nice to lay it out like that. Any questions?
Cool.
All right. You cannot determine the molecular formula from only the percent elemental composition. What we just did was, you can take percent elemental composition and get the empirical formula. Now, you can go ahead all the way and get the molecular formula if you know one more piece of information. If in addition to the weight percent, if you also know the molar mass of the compound, and we'll do an example of that. Actually, we're going to piggyback on this one right here. We went from weight percent to empirical formula like this before. Well, let's just say in addition to the weight percent, which this is what we used, let's say we were also said that the whole molecular weight, the molar mass, well, I'll say molecular weight, the molar mass of the entire compound is 90.1 grams per mole. Well, does this make sense? All I got to do is kind of see how many of this repeating unit for this, whatever mass this is, how many of those I have in 90.1. So it looks kind of like this. When we are given this empirical formula, it could be C4H10O2. It could be, I'm going to write up here because we're out of room. We could multiply by, this is what, 2 times? We could take 3 times, and it would look like, what, C6, yeah, H15O3. We could do it 4 times over here. We just don't know which one it is. So all we're trying to do with that molar mass, that 90.1, is to see, sometimes I call it the base unit, to see kind of how many of these base units we have in 90.1. That's it. So we're going to knock out the molar mass of the empirical formula, which is simply taking 2 times carbon plus 2 times hydrogen plus 1 times oxygen. Okay. And then we're going to take that 90.1 and we're going to divide by that smaller number to see how many repeating units we have. And hopefully it'll be a nice round integer. So if you come up with the molar mass of the empirical formula, kind of the base, it looks like this. So we take 2 times 12.01 for carbon, plus 5 times 1.008 for hydrogen, plus 1 times 16.00. So, and 45 is about half a 90. So you can see that that is our repeating unit of our empirical formula, 45.06 grams per mole. To finish it up then, we're going to go ahead and take the molar mass of the compound that was given, 90.1 grams per mole, and divide it by that repeating unit of 45.06 grams per mole, and get a nice, neat little integer. So this scenario down here, this guy right here, that is the empirical formula. Okay. So you can go from weight percent to empirical formula, easy cheesy. And then to go all the way to molecular formula, you need the molar mass of the compound. So I hated hearing you guys had spent so much time on your homework. So I'm hoping this homework won't be as bad, but who knows, right? But that's right. That's as far as I wanted to get today. So
How nice of you.
sure. It's Friday. And it's symphony weekend. I play in the Southeast Iowa Symphony Orchestra, so I've got concerts in Ottumwa and Burlington this weekend. Should be fun.
Yeah, so I'm excited. There's some pouring in.
I once had a serious